be using a lot, um, right? Hopefully, everybody's familiar with units, stuff like, milli equals 10 to the negative 3. Micro, which is a mu, equals 10 to the negative 6. And then nano equals 10 to the negative 9. Obviously, there's stuff on the positive end. K equals 10 to the 3. And big M is 10 to the 6. Big G, 10 to the 9. So we'll talk about things like kilovolts, megawatts, milliohms, microamps, stuff like that. Okay, so next, what are the basic electrical quantities that we're going to be working with? Okay, the one main one is going to be charge. So charge describes the effect of an electromagnetic field on a component. We'll talk a little bit about what that means. Describes the effect of an electromagnetic field and the unit is called a coulomb. Okay, the next one we're going to talk about is is current. Which we're going to be describing with a lowercase I. And so this is the rate of change in charge. Okay? Mathematically, we can say, right, that I of t is equal to dqt dt. All right? Direction is important. And funny enough, current describes the opposite direction in which electrons flow. So, and this has to do with the way this standard was set back in the day, whenever that was. I don't know off the top of my head, but and a lack of understanding over what exactly an electron was. So current actually describes the flow of positive particles. So if you were to actually think about the flow of electrons, the direction would be opposite of what the current is. Yep.
So in the current electricity, there also positive particles moving?
So you can think of a negative charge as a negative positive. You see what I'm saying there? Now later on we can talk about there are positive particles when we talk about semiconductors, which we call holes. But for all intents and purposes right now, we're just focusing on electrons. So if there were an imaginary particle that anyway, you get what I'm saying. And this is going to come into the calculations when we look at the flow of charge, and then we show the direction of that. It's going to be with respect to a positive particle. If a positive particle would flow in that direction, because essentially what you have is current flows from the positive to the negative terminal of a device. Okay, a passive device. That would dictate, if you just look at basic physics, that should be a positive particle that does that, right? It's attracted to the negative terminal. Whereas the electron actually is flowing from the negative to the positive terminal and is attracted to the positive terminal. Okay, the unit for this is coulombs per second, which is also referred to as the ampere. Okay, next we have voltage. And so voltage is the difference in charge or potential between 2 points. This is also called the electric pressure or tension, although those are really not terms that we use today. And the unit is a volt. Again, just like direction is important for current, polarity is important for voltage, right? We can have 5 volts across a device, positive, negative, okay? Positive, negative, and that means something completely different than 5 volts across the device, positive, negative, okay? For both of these, that's always important. Yes.
So electric pressure and tension, just in physics two, my professor told us to think of it like water pressure or something.
Yeah, there's an analogy. Yeah, there's an analogy you can use for that. It falls apart a little bit when you, well, not a little bit, but a lot when we get into later material. So one way of thinking about it is like a pipe, right? So current would be the rate of flow of water through a pipe. Resistance, which we haven't talked explicitly about yet, would be the diameter or the width of the pipe, right? A smaller pipe would be more resistive. It's harder to get water to flow through that at a higher rate. A lower resistance would correspond to a wider pipe. You could think of a voltage source as a pump, okay, which provides pressure, which then that pressure causes the movement of the water through the pipe. The more pressure you apply, the more voltage you apply, the greater the current is going to be, the greater the flow of water is going to be. And so one of the first relationships we're going to look at is Ohm's Law, V equals IR. Voltage equals current times resistance. And that makes sense when you think about the water analogy, right, where if we flip it around a little bit, I equals V over R. Okay, the flow of water through the pipe is going to be equal to the pressure that you apply to that water divided by whatever the resistance of the pipe is that's preventing its movement. So yeah, I mean that analogy is, I think, a good one for the very, very beginning, but after that point, it can be problematic if you try to carry it on too far, I guess is what I would say. All right, next. So alternating versus DC current versus direct current. So the real definition and difference between the two has to do with whether the wave crosses the x-axis or not. So traditionally, if we're calling this our DC wave and this our AC wave, most people think of this as the only thing that fits the bill of a DC wave, and most people think of this as the only thing that fits the bill of an AC wave. Okay, and we are going to use the terms like that to a certain point. A lot of times we'll say DC, you're assuming that it's going to be a flat line. We say AC, we're assuming it's going to be a sine wave and it's going to cross the y-axis. However, really, direct current, this is also a direct current wave. Okay, a direct current wave can oscillate as long as it doesn't cross the x-axis. Same thing with an AC. An AC doesn't necessarily have to be a sine wave. Okay, so right, anything that looks like this weird looking waveform, right, that would also be considered an alternating current waveform. Yes?
So could DC also be in the negative?
Yes. Yes. As long as it doesn't cross the x-axis. Okay, next, power. So power is the rate at which work is performed or energy is converted. So the rate of doing work or the rate at which energy is converted. That's the general physics definition. We are electrically, right? We know that power is equal to voltage times current. And it's going to be in watts. Or later on, we're going to talk about a unit called volt amps. Yes?
You're saying power is in watts?
Yes.
In volt amps? Oh,
Yeah.
sure, power.
Yeah. Powers in watts. Later on, we'll also use a term called volt amps to refer to it. But as you can see, volt amps is not really a new unit. It's just volts times amps. What's an example of power being consumed by an electrical device? Okay, let's say you have an electric heater, right? The electric heater will have a voltage across it. Let's say it's 100 volts. It'll draw some current. Let's say that's 1 amp, okay? So 1 volt, 100 volts times 1 amp. That means we're drawing 100 watts. That 100 watts of energy is being converted from an electrical form into heat, and it's emitting that heat. Light, another example, right? If you have a 60-watt bulb, which you really don't see anymore because all the bulbs are LED, but back in the day when we used to have 60-watt bulbs, right, the nominal value would be that the light and the heat emitted would would account for 60 watts of energy conversion. Energy, right, is energy. We know what that is. And it can be defined, well, not can be defined, is defined as the integral of power over time. So there may be one or two questions that ask you to calculate the total energy that's consumed by a component. So all you would have to do is calculate the power at specific points in time, and then either use a discrete sum or use an integral if it's a continuous function, and calculate what the total energy being consumed is. Okay, so next. So I have you can see here in my previous notes, this is from another year, I did go through and talk about the whole, can we think of an electric system like a pumped water system? I kind of already talked about that, so I'm not going to draw the whole thing again. But right, the analogy does apply where voltage would correspond to pressure, resistance would correspond to anything that resists the flow of water, which could be debris in the pipe or it could be the width of the pipe, and then current would be analogous to the rate of power flow. Yeah. Yeah, these are available. If you go here, you'll see, so lecture notes from board. I will, additional source. So I have like 30 versions of the notes. I will put this is the 2016 version of the notes. I'll update it so that link, which says lecture notes from board, so that'll be the 2016 notes. So you click there, it'll just be a zip file. And all these notes, the ones that I'm writing right now on the iPad, they'll be available on the website as well. I'll create a new link for that. So if you do find yourself watching the videos, I'm slowly going to figure out what the best way is to get a good view of the board. Sometimes it can be a little bit difficult to do that, but you can use the PDF of the notes along with it and kind of go along, because you may not be able to see 100% of everything from the way that it's zoomed in. Okay, so continuing on, Ohm's Law. So Ohm's Law is going to describe the relationship between voltage and current. So what we see is that voltage is equal to current times resistance. And it can also be flipped around, right, to say the opposite, which is current equals voltage divided by resistance. Now, in this case, right, we have to be cognizant of what the polarity of this is, and that's going to have an effect on what the direction of this is. Resistance does not have a directional component, a polarity or anything like that, a sign. For our intents and purposes, for our purposes here in this class, negative resistance doesn't exist. There's certain mathematical things you can do where they represent resistances as negative values, but that's not going to play a role here. You've heard the term short circuit before. Short circuit, aside from being the awesome robot comedy movie from the 1980s, which you guys who has seen Short Circuit? No one's seen it. It's actually really bad, so don't go see it, but it's like a campy movie. So a short circuit denotes a short between what should not be grounded and is grounded. So if I were to take a fork, stick it into one of the sockets here, right, that would provide a low impedance path, low resistance path between the positive and the negative. And so what happens is you're going to get a ton of current flow, okay? Right, because if you have current equals voltage divided by something very close to zero, what you end up with is that. So the reason why short circuits are problematic is because, right, they result in huge spikes in current, which are going to be very dangerous if anyone alive with a beating heart is involved, but is also going to be very dangerous to equipment. It's going to blow your fuses, and most likely it's going to create a thermal problem for almost anything that's in that path. So more times, 99% of the time, we don't want any of our paths to have a zero resistance or very, very low resistance. Okay, now how do we figure out what the direction is of this stuff? So we are going to use something called the passive sign convention. So the passive sign convention is a way that we can relate the direction of current to the polarity of a voltage. Is it still recording? Actually, let me see if I can zoom in a little bit better. Actually, you can see the board pretty good. It's not that bad. So if we have let's take a component. I'm going to use a resistor just for demonstration, but it doesn't have to be a resistor. So if we have a resistor, and then we say that the voltage looks like that, positive, then negative. The passive sign convention tells us that the current will flow in that direction. So, if we're using V equals IR, those are the directions. Now, obviously, one of these will have to be defined a priori, meaning that it'll either be told to you by the schematic, or by the problem, or you'll have to just assume what the direction is. Yes.
So basically, it's just telling you that current's flowing from the positive to the
Yeah, for a passive component only. Passive component means that it's absorbing energy. It doesn't have any other energy source coming into it. For active elements, like a voltage source, I don't want to get too confusing right now, but for a voltage source, you'll see that current will flow in the opposite direction. Okay? But it doesn't mean we can't use the passive sign convention. What will end up happening is we'll use the same directions, we'll use the same V equals IR. You'll just end up with a current that's flowing in this direction with a negative value. So the convention will work regardless. And we'll just take into account the deviations from it using the sign. And that's all that the passive sign convention tells you. It just tells you that whatever number you get is referred to this direction. It doesn't tell you that the current is positive in this direction. Right? You see what I'm saying? This voltage could be negative 5 volts. This current could be negative 2 amps. But if you don't set the direction, you don't know which way negative 2 is. Okay? And when we get into some examples, this will be made more clear what that means. Okay. Power consumed by an element. by a passive element. So P equals V times I. We know that. We can replace our I with V divided by R, right? That's just coming from Ohm's law. Up above here. And so that gives us a different form of this, which is V squared divided by R. So we can define, if we do another substitution, we can also get I squared R. We'll also get that form of it. So if you want to calculate the power being consumed by a resistive element, you can use either V squared over R or I squared R. And the passive sign convention also tells us that power is consumed / drawn from the system. So another part of the passive sign convention is saying, okay, if our voltage polarity looks like this, our current direction will look like this, and whatever value of P we calculate is P being drawn from the system. Again, you can still get a negative value for that P, which in that case means drawing negative power, which is the same thing as injecting power into the system. Okay, next, and I know we're kind of just flying through a whole bunch of different topics, but these are sort of like basic concepts, vocabulary, you know, just all the stuff that we need to get in your heads before we can dive into some of the real problems and stuff like that. So impedance. We keep saying V equals IR, V equals IR. That's actually not the full story. Okay, that's a description that we can use for DC systems. But for AC systems, we're going to have to use a version that looks like this, which is actually V equals I times Z, where these are all vectors, one way of representing the AC waveforms. Okay, that's the same as saying I times R plus JX. So have you guys used complex numbers before? Vectors, any of that stuff? You should have seen it. We're going to dive back into what all this means when we get to AC systems. So for more or less, I'm going to kind of give this to you right now. Just be aware of what the values are, what they mean, and then when we get to AC systems closer to the end of the semester, we'll give some more context. So the real portion of impedance is called resistance, and the imaginary portion is called reactance. And so because in DC systems, for whatever, we're not going to discuss it yet, for DC systems, the imaginary components of all the waveforms go away. And so that's the reason for a DC system we can say V equals IR. Okay? But if we're talking about an AC system, it's V equals IZ, where Z is R plus JX. Okay. And so this is called impedance. I will ask you to please just know these values. This is just something that everybody who is doing any sort of engineering work should know. There's also an inverse of that. So you'll see that Y is equal to 1 over Z. This is called conductance, and that has two parts as well. Sorry, it's called admittance. So this is called susceptance, and this is called conductance. And this is called admittance. So what is this all, when we put it all together for a second, what does it mean? Impedance for AC systems describes the limiting of current. The higher the impedance is, the lower the current will be. The impedance is made of two different components. There's the real component, which is resistance. There's the imaginary components, which is reactance. Then we have the opposite of that, okay, or the reciprocal. Admittance is 1 over Z. Just another way of saying the same thing. So a high admittance means a lot of current will flow. Now that has two components as well, conductance and susceptance. This is almost like, I would say, like a trivia question, but for ECE. Know these values. It will come up on a quiz. I always ask it every year. Very simply, 4 blanks. Give me the real and imaginary components of resistance. Give me the real, of impedance, and give me the real and imaginary components of conductance. Well, see, it applies to, again, the thing is, in DC systems, there is no imaginary component. So that's the reason why we take V equals IZ and we call it V equals IR, because this portion goes away. Same thing here. We could say I equals Vy, but in DC systems, when we would just say V times G. You will see the term conductance used in DC systems. Right, it's all because essentially what this represents is phase shift, or represents, part of it is representing phase shift in AC waveforms, and so since there's no phase shift in DC, it doesn't have any meaning. Yeah.
So, is the cause of this because it like goes up and down?
We'll get into it. It's a mathematical thing.
So, just
Yeah.
because it all cancels out in DC because it's a constant, so what does that?
So if you think about it like this, in DC, for DC waves, there's only one thing you have to describe, which is amplitude, or whatever the average value is. Okay, in AC waveforms, we normally describe it using two values, which is going to be the amplitude as well as the phase shift, how it's moved from right to left. And so that makes the math a little bit more complicated. Part of that we represent as the imaginary value. Again, because there's no, I don't want to get too sidetracked in this, because there's no phase shift in DC, right, moving to the right or left doesn't matter. It's the same thing, okay? There is no imaginary, in the mathematics itself, the imaginary portions just all fall away.
So it's like you're working on like an extra dimension.
Yes, there's an extra dimension when you're talking about AC. Yeah. Mm-hmm.
If it's oscillating but not going below the axis, would that still let everything cancel out?
No, no. And this is, again, where I'm sort of using the less than accurate way. I mean, we're gonna use AC to mean oscillating sine waves crossing the x-axis, and DC to mean straight lines. But yeah, that's sort of where we're using it a little bit loosely, that term. But we're not going to, I mean, the other thing is I also don't want to start talking about things that we're never going to deal with. For example, systems that use oscillating DC signal, you don't see that very much, and maybe in signal processing or something like that, but I mean, we are also going to kind of stick to the cases that make sense for application and not just go off on them. Well, what if you had, like, a power supply that was given a sawtooth wave, and how would you deal with that? And that's like a, maybe a question for another day. Okay. So, next thing. In the book, they talk about something called Telegon's theorem, which I spelled wrong, I think, but whatever. I'll have to. And so Telegon's theorem has to do with conservation of power or conservation of energy. Hopefully you are all familiar with the principle of conservation of power, conservation of energy, right? Energy can't be created or destroyed. It can only be converted from one form to another. And so we got that, and that applies to our electric circuit. So let's say we draw something that looks like this. And I'm just going to use boxes for the other components because for right now we don't really care what they are. So we have elements A, B, and C. Okay, what we should see, or what we know, is that the power dissipated by A plus the power dissipated by B plus the power dissipated by C will sum to 0. And so this is the essence of the theorem. Now, in order to properly define PA, PB, and PC, we have to know what the polarity is and the direction of current, referential direction of current is for all of these components, right? So let's write those out. We're going to use our passive sign convention. So what we know is that VC, I'm just picking this direction. I could go the other way. Again, for the passive sign convention, it's really I and V agreeing with each other. So if I choose V as this polarity, that means I will have that polarity. I'll use a similar one here, VB, which means that IB will have that direction. You'll see over here that we're using a different direction polarity of the component. That's no big deal. All that means is so our VA will be plus minus. Our IA will have a direction that looks like this. So you'll see that IA, that direction conflicts with IB and IC. IB, IC both go like this. IA goes like this because we flipped our polarity. And this makes sense when we get into later problems. You'll see that this is an active component, right? This is a source. So this is injecting power into, we'll see this is injecting power into our system. And then these are assumed to be passive components, which are drawing current from the system. So now, how do we define our PA, PB, and PC? So pretty straightforward. We're just going to use our passive sign convention. We know that PC will be equal to VC times IC, right? Because if we obey that passive sign convention, it's just P equals V times I. PB will be VB times IB, and PA will be VA times IA. So that's Telegon's theorem. Now, peeking a little bit forward, looking forward to KCL, Kirchhoff's current law, let me ask you a question. Does it make sense that the current flowing in this loop should be the same here, here, and here? Think about the water example, right? If there's no place for the water to go, then it has to keep flowing in the loop. So Kirchhoff's current law actually tells us that. What it says is that IB should be equal to IC, should be equal to the negative of IA, because you see IA is pointing in the other direction. So we can define a single current and I'm going to call it Ix, is equal to negative IA is equal to IB is equal to IC. And so Ix would have a direction flowing like that. And so if I take that and I plug it into this expression right here, what that will give me is something that looks like this. Ix times VB plus VC minus VA equals 0. Right? VA will be negative because the relationship between IA and Ix is negative, right? This will be replaced with Ix, this will be replaced with Ix, this will be replaced with negative Ix. Yeah?
When you say that negative IA equals IB, you mean the absolute value of negative IA equals IB? Because when it's the...
We haven't defined a value yet. So it's just the symbol itself.
So if you just had the value of IA...
It's not the absolute value. It's not. It is the value of IA. Because what you'll see is in the end, we'll calculate a value of IA. And if you want it to match Ix, it will be negative times whatever the value, which will probably be a negative value times IA. Okay. So, and then, right, you could actually just cross out Ix. So Telegon's theorem, conservation of energy, conservation of power, tells us that the powers have to be equal. And you'll see here the negative sign it makes sense because you'll have power coming into the system here and it'll be drawn out here and here. So if you have 3 watts coming in, you'll have 2 watts lost here, you'll have 1 watt lost there, and it all evens out to 0. Okay, now, let's go back and quickly talk about, because we used Kirchhoff's current law, but we didn't really introduce it. So Kirchhoff's current law, what it says is that all of the currents entering a node have to sum to 0. Or another way of thinking about it is all the currents entering a node have to equal all the currents leaving a node. So let's draw some pictures that tell us that. Okay, so and what is a node, furthermore? A node is any point that connects 2 branches. So this would be a node, this would be a node, 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 and that would be a branch. Okay, so if we take a look at this right here, we see we have an IA. These are different IA, IBs, ICs. And so if we wanted this to work out, one example of values would be we have 2 amps, we have negative 1 amp, and we have negative 1 amp. Okay, all of those sum together to be 0. Another way of looking at it is saying, which is really saying the exact same thing, it's just, again, playing with the directions in which we have defined our currents. So now in this one, I've defined the directions of IA and IB differently. And so now in this same case, it will be 2 amps, 1 amp, and 1 amp. Again, right, the left and the right are saying the exact same thing. Negative 1 amp heading into the node is the same as 1 amp leaving the node. Okay, so 2 plus negative 1 plus negative 1 equals 0, or 2 minus 1 equals 0. So the two definitions are going to be, right, the sum of all currents entering the node or we can say it'll be equal to the sum of all currents entering the node minus the sum of all the currents leaving the node. Does that make sense? It's going to take a little bit to get comfortable with the idea of the directions and the polarities and how it's all sort of wishy-washy to a certain point. You can do it one way. You can flip all the directions and do it, and you would end up with the same answer, obviously with the values being opposite, and then you would have to account for the directions. Yeah?
Let's not suppose we had some sort of problem that was like that, and we did it the opposite way that you're supposed to. Would that still be full credit?
So more times than not, what I'll do is I'll give you at least the direction of the value I want you to solve for, or the polarity, just to make it easier. But if I don't, then no. I mean, there's no penalty. Obviously, there's no right way to choose any of these things. Okay, now, Kirchhoff's voltage law, actually, we can take directly from here. All right, so what does that mean? So if you look at what it's saying here, Taligin's theorem directly leads us to draw the conclusion that for a loop, a closed loop, all of the voltages must sum to 0. Okay? The powers must sum to 0. In a given loop, the currents must all be equal to one another. Therefore, the voltages must also sum to 0. And so that's what Kirchhoff's voltage law, KVL, is. It says that, now, this can work for any loop in the system. For example, let's say I draw a system that looks like this. Okay? And it has a second little mini loop over here. And I define a bunch of these voltages. So I'm going to call this voltage A, call this voltage B, plus minus, voltage C, plus minus, voltage D, plus minus, voltage E, plus minus. There's different loops in here. There's loop 1, there's loop 2, there's a bigger one that goes all the way around it, which is loop 3. And so KVL will apply for all of those loops, any of them. So if we were to write it out, what we would see is if we're looking at loop number 1, VA, and so when we're writing out KVL, we have to pick a referential. I know we're almost out of time here. We have to pick a referential direction. So if we're going to sum these all together in this loop, they have to have the same polarity. So if we're picking this polarity as positive, that means it will be VA minus VB minus VC. We can do the same thing for loop number 2. Again, what I'll do is I'll choose VC as the positive direction, which means VC minus VD minus VE equals 0. And then lastly, where we'll end, you can do it for the outer loop, which I'll choose VA to be positive. So that means that VA minus VB minus VD minus VE equals 0. Okay? So this is a rule that we can apply to any loop in the system. So we'll stop there, and we'll pick up next time. All right, thanks. Have a good first week.